In early 2026, a 27-year-old integer overflow vulnerability in the OpenBSD TCP stack was compromised. It was not identified by a human researcher, but instead autonomously breached by a single artificial intelligence model. This same model subsequently compromised a 16-year-old flaw in the FFmpeg media library, a vulnerability that had survived 5 million iterations of traditional automated testing. Traditional security tools failed to find these flaws because they act as execution engines. Fuzzers and static scanners rely on pattern matching and brute force pathing, but they lack the ability to understand the context of the code they are testing. Claude Mythos Preview represents a transition to semantic reasoning. It reads source code to understand its intended logic, allowing it to identify discrepancies between the developer's intent and the actual implementation. Identifying a vulnerability in a source file is only the first step. Synthesizing a working remote code execution exploit requires the model to navigate and bypass modern defenses like sandboxes and memory-safe virtual machines. To understand how this works, we have to look at the specific architecture of Anthropic's unreleased model, Claude Mythos Preview. When an adversary can autonomously chain exploit primitives, defensive measures that rely on manual friction rather than hard architectural barriers face a significant scalability problem. A frontier reasoning model is a text predictor. It cannot exploit an external system without an execution harness to bridge the gap between logic and action. The Anthropic Red Team utilizes an agentic scaffold, placing the central Mythos model within an isolated, air-gapped container to prevent unauthorized network access. Inside this container, the model is provided with the raw source code of the project under test. A middleware component, the Claude Code Agent, acts as the translation layer, turning the model's logical reasoning into executable terminal commands. Finally, the container includes standard development tools, compilers, and debuggers, allowing the model to test its hypotheses in a live environment. This triad of source access, agentic translation, and local execution gives the reasoning engine a digital body to manipulate state iteratively. It is the execution harness, and not just the raw model weights, that enables the system to function as an autonomous penetration testing loop. Manually auditing a massive repository with a heavy inference model is computationally expensive. Efficiency requires a rigorous prioritization strategy. The harness employs a parallelized search protocol, where the model assigns a vulnerability likelihood ranking from 1 to 5 for every file in the codebase. Files containing simple constants or boilerplate code are ranked as a 1 and are excluded from the processing queue. Files that parse raw data from the internet are ranked as a 5, marking them for immediate analysis within the agentic loop. Once a target is identified, the model reads the code, hypothesizes potential flaws, and writes a proof-of-concept script. The agent N executes the script against the compiled project and monitors the environment for a crash or a successful exploit. If the test fails, the model uses the debugger output to refine its understanding and rewrite the exploit without any human prompting. This parallelized approach allows the model to analyze codebases with a degree of thoroughness and speed that human auditing teams cannot replicate. We can see the results of this loop in the model's discovery of a 17-year-old remote code execution vulnerability in the FreeBSD NFS server. The goal was to synthesize a return-oriented programming, or ROP, chain that would append an attacker's SSH key to the root user's authorized keys file. However, the FreeBSD server imposes a strict constraint. Each remote procedure call is limited to only 200 bytes. The 20-gadget ROP chain required for the exploit was over 1,000 bytes long, far too large to fit in a single transmission. Under these architectural constraints, achieving execution in a single shot was physically impossible. The model adapted by autonomously dividing the 1,000-byte payload into 6 distinct sequential chunks. It used the first 5 requests to write the data into unused kernel memory piece by piece, effectively bypassing the per-packet size limit. The 6th packet then triggered the system call that executes the fully assembled payload, granting the model root access. No human provided guidance on how to split this payload. The model solved the spatial constraint entirely through its own reasoning. This highlights the core threat: the model's ability to dynamically alter its methodology to overcome specific system hurdles on the fly. On the Linux kernel, Mythos demonstrated the ability to chain multiple independent vulnerabilities to defeat defense in-depth measures. Kernel Address Space Layout Randomization, or KASLR, randomizes memory locations to make exploits unreliable. Mythos first used an out-of-bounds read vulnerability to intentionally leak a kernel pointer from memory. By calculating the offset from that leaked pointer, the model successfully determined the kernel's base address, bypassing the randomization. It then used a second, separate vulnerability to locate a critical process credential structure within the kernel. Finally, it applied a use-after-free write paired with a precise heap spay to overwrite those credentials and gain full root permissions. This demonstrates that defenses based on layout obfuscation are insufficient against an adversary capable of autonomous vulnerability chaining. To understand the significance of this shift, we have to look at how Mythos performs against the previous state-of-the-art. On a benchmark using the Firefox JavaScript engine, Claude Opus 4.6 successfully generated an exploit only twice. Mythos Preview succeeded 181 times. On the SWE Bench verified metric for real-world software engineering, Opus 4.6 scores 80.8%. Mythos reaches 93.9%. But these capabilities exist on a jagged frontier, where progress is significant but inconsistent across different tasks. While Mythos is exceptionally effective at creating exploits, it cannot yet autonomously deploy verified production-ready patches to live systems without human oversight. This creates an operational asymmetry. The model can find and exploit vulnerabilities far faster than a human team can patch them. This imbalance is why Anthropic has restricted access to the model through Project Glasswing, providing it only to vetted defenders and critical software maintainers. As autonomous models remove the barrier of manual effort, security relies less on the difficulty of finding a bug and more on the structural resilience of the code itself.